Exoplanets, that is, planets orbiting other stars, are a really hot topic in astronomy right now. Although the science of exoplanets kicked off back in the late 1990s, the success of the space telescopes CoROT and KEPLER has really accelerated the field. Back in the 90s, we were discovering 1 or 2 planets a year on average. Now, thanks particularly to KEPLER, hundreds of new planets are being confirmed every year, with thousands more candidates being found. Kepler's discoveries haven't just been prolific, they've also transformed what we know about exoplanets. There are several methods used to detect planets, and in the early days they all showed that the exoplanetary populations were dominated by really massive companions. Most of them were more massive than Jupiter, and only 15% were less massive than Neptune. Then Kepler came along and showed that most planets are actually quite small. In fact, only 15% are larger than Neptune, and Earth-sized planets are more common than we thought. The most common planets of all are so-called super-Earths, or mini-Neptunes. These are planets with no direct analogues in our own solar system, so we're not even sure what they look like. They could be large rocky planets or water worlds with a deep global ocean on the surface. We don't know. A lot of theoretical work's being carried out at the moment to predict the composition of the huge tally of exoplanets that Kepler has produced. One thing is for sure, the gas giants like Saturn and Jupiter are comparatively rare. In retrospect, it's easy to see that the early discoveries were dominated by really big Jupiter-sized planets, simply because big planets are easier to find. But Kepler was built to spot the planets that are hard to find. Specifically, it was designed to determine the number of Earth-like planets in the galaxy. Its great sensitivity has led to the discovery of some pretty exciting planetary systems, such as Kepler-11, a 6-planet system, and Kepler-186, with 5 planets smaller than 1.5 Earths. And one of these is particularly interesting. Kepler-186f is the most Earth-like planet we've found so far. Kepler looked for planets using the transit method. When a planet passes in front of its star, it blocks out some of the light, and the telescope detects this brief decrease in brightness. However, the planet's orbital plane has to be aligned just right with the telescope's line of sight for this to work. And assuming that exoplanets' orbital axes are randomly distributed in space, then the geometric probability of a transit is only about 0.5%. So to find a lot of planets, you need to observe a lot of stars. And of the more than 500,000 stars in Kepler's field of view, around 150,000 were chosen for observation, and Kepler observed all of these stars simultaneously. When an exoplanet is found, the transit itself is used to characterize the planet. In particular, the transit depth tells you how large the planet is in relation to its host star. But there's a problem, in that the sizes are only relative. An observed transit could be the signature of a big planet orbiting a big star, or a small planet orbiting a small star. Either way, you'd observe the same signal. You have to know something about your star to constrain the radius of the planet. To solve this, Kepler has an input catalogue containing information on hundreds of thousands of stars in the telescope's field of view. One of the catalogued properties is stellar radius, which is then used to calculate the planetary radius for each detected exoplanet. And in this way, scientists are able to characterize the vast population of exoplanets being discovered.